Today we are continuing with probability, but lesson 12.2 is conditional probability. Okay, so still the basic idea of probability, but when there's a condition involved. Okay, the probability that this happens given that this is true. Okay, so probability based on a condition. So we're going to go through kind of the setup and look at some different examples, of course. So, definition of conditional probability. The probability that an event B will occur given that another event A has already occurred. Now, notation-wise, you see some notation here, right? The notation, it's probability of B, and then there's a vertical line, and then an A. That is read the probability of event B given event A. So the probability of event B happening given that A is true. For any two events, A and B, in the sample space, and we have a formula here. So the probability of B given event A, we set up as a fraction on top. You're doing the probability of A and B. Over the denominator, you're doing the probability of A, which is the condition there. So that's conditional probability. Okay, so that's the formula you'll want to become very familiar with. Give us a little bit of practice, and I think you'll, get used to setting it up pretty quickly. So I'm going to kind of take us through, on this first example, I'm going to take us through two different ways to set it up. The official way, and then what I would recommend is kind of the shortcut way. Okay, so let's look at this one to help us understand it. A student committee is being formed to decide how after-school activities will be funded. The committee members are selected at random from current club members. The frequency table shows the current club membership data. So we have information about Monday club memberships by grade. So you see sophomore, juniors, and seniors, and the clubs, drama club, science club, art club. And then you'll notice there is a total column in this chart. Okay? Now, our question is, what is the probability that a member of the art club selected at random is a junior? Okay? When we're asked this, okay, understand probability that the member of art club selected is a junior. We're asking, what's the probability that this person is a junior? What's the condition? What's probably that they're a junior given that they are a member of art club? So if I write this out, we're doing the probability that the student is a junior given they are a member of art club. Okay? So that's what that problem is. They put it in words for us, but when we put it as a setup there, that's what we're looking at. So the probability that the student, probability that they're junior given that they are already in art club. Now, what's that say about our setup? If you go back and use the formula. So the idea of, what was it? Probability of B given A. So, I won't always put those B's and A's on there, but I thought it might be helpful here. What are we going to do? Our setup is a fraction, right? On top, it's going to be the probability of B and A, which, what is B and A in our case? I don't know. I don't know the numbers. Very possibly, but if I was just trying to put it in words. I'll get to the numbers here in a moment. On top, we're looking at the probability that the student is a junior and an art club. Okay. So probability of being a junior and in art club, and it was given that they're already a member of art club. So on bottom, we're going to do the probability that they are in art club. Now, and this is where I said, I'm kind of taking you the long way here in a moment. I'll show you the short way here, too, of course. Probability of a student being a junior and an art club. What is that looking like? Junior and an art club, what'd you say? 16. Now, officially it says probability, doesn't it? So 16 out of how many?
Oh, wait, like 40?
No?
Oh.
The 115. Okay, the total. As I said, I'm going to shorten this up here in a moment, but the idea that officially this is 16 over 115. That's on top. On bottom, what's the probability that the student is an art club member? So what's the probability that they are a member of the art club? So there are how many students in the art club? 58. Out of how many total? 115. So officially, this is 58 over 115 in the denominator. Officially, we have a fraction divided by a fraction. Well, what are you guessing this is going to clean up to be? The 115s are going to cancel. And this is going to clean up to be just 16 over 58, which is what Michaela wanted me to put it first. Okay? Now, officially, that's how conditional probability works. It's the probability divided by the probability. So, yes, it's a fraction divided by a fraction. Okay? Now, before I circle that, does 16 over 58 reduce? I see that they're both even, so that tells me something. Which, by the way, do you have calculators at your desk? Because you're probably going to want them, right? If they're both even. We know they at least divide by 2. What does this reduce to? Okay. 8 over 29. Okay. As I said, I did the long way. You guys are looking at it saying, really, Mrs. Sargent, fractions and fractions. Did we have to look at that 115, though, in this scenario? No. Okay. And had we done, if you want to seriously work this out, fraction divided by a fraction, keep change flip, your 115s will work out, or will cancel out. Now, what I would just do, I'm not going to necessarily have you guys do the fractions. I would have just said, okay, let's just do the juniors and art club on top, the total art club members on bottom. So could we have just gone the 16 over 58 and then reduced from there? Most definitely. And that's what I'm going to encourage you to do as we go through this. Okay? Where basically we will not worry about the 115s. Okay? So, I was going to write this out a different way, but we've got lots of other examples, so we'll worry about the other examples. Questions on this one, then? Okay. Now, who wouldn't have room to write? So, I have the chart up here again. We have some more problems to look at. Okay? So, I'm not going to fill that in again, but let's look at some other problems. Figure this out. What is the probability that a member of the drama club is a sophomore? So, notice, they already have this written out for us, yes? They're asking us what's the probability that a student is a sophomore given they're a member of drama club. So the condition is given they're a member of drama club. In words first. What are we going to put on top? On top is the probability of sophomore and drama. A and B, right? So on top of my fraction, it's going to be the probability of sophomore and drama. What about my denominator? Well, no. On top, it's probability of sophomore and drama. I guess it depends what total you're talking about. The total drama, right? So basically the probability that a student is a drama student. So probability of the condition. Now, the shortcut. don't worry about probability, just, okay, what do you know about students that are sophomores and in drama? Okay, but I'm going to skip the 17 on this one. Okay, sophomores in drama? No, just the 3. I'm just trying to get you to how many students are in drama and sophomores. Over, when I say probability of drama, how many students are in drama? And there's the 17. Okay? You're just ahead of me. That's what it is. Does 3 over 17 reduce? No. Okay? Are we okay with this? Okay. Let's try the second one, or the next one. What's the probability that a sophomore is a member of the drama club? Sounds like the same question, doesn't it? But they flip things. So now it's, what is the probability that this person is in drama club, given that they are a sophomore? So in terms of words, how does that change my setup? On top, it's still probability of A and B. So on top, it's going to still be probability of, I'm going to write it as drama and sophomores this time. But basically, it's going to be all your drama students and sophomores. What's my denominator this time? What's my condition? It's probably that they're a member of drama given they are a sophomore. So we're going to divide by probably they're sophomore, or the sophomores. Let's look and see how this compares. When I say probability of being a drama student and a sophomore, basically, how many students are in drama and sophomores? And that is what? Still 3. Didn't change. Over, probably the student is a sophomore. How many sophomores do we have? 36. And what do you know about 3 over 36? It reduces to be 1/12. So not the same answer, is it? Okay, and that's a good thing to notice. But that's what we need, that's what we're looking at here is how are these different? So our third part of this says, okay, is the probability of being a sophomore given they're a member of drama club the same as the probability of a student being a member of drama club given they're a sophomore? Well, we just did the math. Are they the same? They're not the same, are they? We got 2 different answers. Why aren't they the same?
Because one you're doing total overall sophomores, and you're doing total.
Yeah. In both cases, we're looking at sophomores and drama. But in the first one, we compared it to the total number of drama students. In the second one, we compared it to all sophomores. Okay? So, obviously, don't need to state, but no, they're not the same. We already have the proof there. And what I will say is probability of sophomore / drama, that compares sophs and drama to all drama club members. And yes, sophomores have become softs because it's shorter. So, probability of soph given their drama club member compares softs and drama to all drama club members. probability of drama, given they're a sophomore, well, it still does the same top, right? It still talks about comparing the sophs and drama. But this time it's comparing to all sophomores. So it's all about what that condition is. Okay. So that's kind of a little bit of an introduction about conditional probability. Remembering, if you get your setup, I don't think it's too bad. I don't know, you guys can tell me. We have a unique combination. Several of the people we have out today are more of the talkers, aren't they? I still got Michaela. She'll still talk to me. Okay. Ready to look at the next one? No? Okay. So start reading about Diego. Diego wonders whether the amount of sleep he gets is related to the amount of coffee he drinks. For about 10 weeks, he records how many cups of coffee he drinks each morning and how many hours he sleeps that night. Rounded to the nearest hour. Okay. Based on this data, what is the probability of Diego drinking or getting 8 hours of sleep given he drinks 0 cups of coffee? And then in the end, we'll round to the nearest whole percent. Okay, so there's your setup. What's going on top of my fraction? Okay, so on top it's going to be the probability that he gets 8 hours of sleep and drinks 0 cups of coffee. So on top, it's always both of them together. On bottom, what's my denominator going to be here? Probability that he sleeps or drinks. Okay. It's the probability that the second piece, which is the 0 cups. So probability that he drinks 0 cups of coffee. Know that setup, okay? Now, easy part on top. 8 hours and 0 cups. What data do we have if he gets 8 hours of sleep and drinks 0 cups of coffee? Okay. Looks like that happened 12 times. Probability that he drinks 0 cups of coffee. How many times did he drink 0 cups of coffee? 22. What do we know about 12 over 22? 6 out of 11. Now, officially, it does ask us to round our final answer to the nearest whole percent. So, if you go to a decimal, this is what? Five, 4, 5, 4, 5, 4, 5, 4. Is it repeating, I think? What is this when we go to a percent? (54.54%), which rounds to be about what as a whole percent? 55%. So, probability that he will get 8 hours of sleep, given he drinks 0 cups of coffee, is about 55%. Okay. On to the next page. The top of the next page here, we talk about the connection between conditional probability and independent events. Remember, we introduced independent events yesterday. 2 events are independent if the first does not affect the second does not affect the first. Okay. Now, how this affects conditional probability. Let A and B be events where neither probability is 0, is what that's saying here. If the events are independent, then the conditional probability of B equals the conditional probability of B given A equals the probability of B, and the conditional probability of A given B equals the probability of A. Okay, that's a lot of mumble jumble, right? Here's the synopsis. If the events are independent, what has to be true? 2 things have to be true. Probability of B given A has to equal probability of B, and reverse it, the probability of A given B has to equal the probability of B. Or excuse me, probability of A. That's kind of our test. Okay, our test to see if 2 items are independent. Now, the second variation down here, it's just flipping the order. Okay, it's just writing it in the reverse order. And so it's saying the same thing. And again, if those probabilities are true, the events are independent. Now, what we're going to do is we're going to use this test for independence. We're going to decide, in the scenarios they ask us, if the events are independent based on looking at these 2 probabilities. So when I'm asking you to do that, you're always going to be finding these 2 things. This will be our proof. They both have to be true for the events to be independent. Okay? So let's go look at, what is it, parking garage? Okay. On the parking garage. This table shows the vehicles in a parking garage one afternoon. A vehicle in the garage will be selected at random. Let B represent the vehicle is black, and let V represent the vehicle is a van. Are the events B and V independent or dependent? In other words, are the events that the vehicle is black, the vehicle is a van, are those 2 events independent of each other or dependent of each other? Okay, now, I don't want your, oh, well, I think it's this answer. Mathematically, I just talked about a test up above, right? We're going to work on this test here. So we're going to test and see if they are independent. And so if you look at the idea of what it has set up there, we're going to have to test. What do we have? We have B and we have V. I will try to enunciate. So first one, probability of B given V. And then we'll reverse this in a moment too. Probability of B given V. Okay, in letters right now. I'll get to numbers in a moment. On top, when we do this conditional probability, is the probability of what? Of both of them. So it's probability of B and V on top over, which one goes on bottom? The condition, which is what? Same thing we did on the front page. Condition, which is the second one. So we're going to put V on bottom. Okay. Let's go ahead and do this math while we're here. What's the chance of the vehicle being black and a van? How many? 3. What's the chance the vehicle is a van? 3. And what's 3 over 3? 1. Okay, so right there, that's the probability of black given it's a van. Now, go back to your test up above. I'm going to bump back to the last screen for a moment. What do we have to see if that equals? Probability of B given A, we want to know if it equals the probability of B, the initial probability there. So, interpret that to ours, and that means I want to check what is the probability of the first one, which is B. I'm going to squeeze it in right there if I can. Now, this is just basic probability. What's the probability of B here? So, probability the vehicle is black. What do we know about black vehicles? There's 13 of them. Out of how many? 22 total vehicles. What do we know about those two probabilities right there? One and 13/22. Are they the same? No. So I can make the statement that the probability of black given it's a van does not equal the probability it's black. Okay. Now, right now it's looking like it fails the test for independence. But I'm going to check the other one too. Okay, get us in the habit of checking both. So let's reverse the scenario. We just did, does the probability of B given V equal the probability of B? Now flip it. Instead of doing B given V, let's flip it and make it V given B. Okay? So we're going to check the probability of V given B. And then when we get over here, we're going to check and see, does it equal probably the first one, so probability of V. Okay. On top, what's always on top? It's the probability of both of them, probability of V and B, divided by, for conditional, divided by the probability of the second one, so probability of B. Okay, guys, we already talked about probability of B and V. How many vehicles that are black do we, or not vehicles, vans that are black? I already used that 3 once, we're going to use it again. Divided by, how many black vehicles do we have? So there we have 3 out of 13. Okay, that doesn't reduce, that's 3 out of 13. We're going to compare that to the probability of the initial probability. So probability the vehicle is a van. How many vans do we have? 3 vans out of how many vehicles? 22. Guess what just happened? So 3 out of 13 and 3 out of 22 equal each other? No. So again, we can make the statement P probability a vehicle is a van given it's black does not equal probability the vehicle is a van. Now, here's what we know. Because of these two statements not being true, if both of those statements are true, we'd be able to say the events are independent. Since they're not true, what's the opposite of independent? Dependent. We know events B and V are dependent. B and V are dependent. Okay, they failed the test. They ended up not being equal to each other. They failed the test. They are dependent events. And in this scenario, that should make sense, because if you look, all the vans were black, weren't they? Okay? All the vans were black. Now, the question may be out there of, could we just have stopped after the first one failed? Yeah, probably. Okay? Once you get one that fails, assuming you didn't make a mistake, then it doesn't really matter because they both have to be true. Okay? Let's try one more variation here. Let R represent the vehicle as red, and C represent the vehicle as a car. Are the events R and C independent or dependent, and explain? Okay. What do you want to start by looking at? Probability of? What'd you say? Well, so vehicle is red, given it's a car. Okay. Question?
Conditions, but them again.
English.
There goes the bathroom.
Can you wait like 10 minutes?
Okay.
Is that okay?
With those kids.
Okay. Probability of R given C. So if we're looking at probability of red given it's a car. On top we're doing what? On top is always both. Divided by the denominator, which is always the condition, the second piece. What do we have on top here? How many vehicles are red and cars?
7 and 5. I said that.
Okay, that would make sense then. Red and cars is just going to be 5. I'm all confused. Over probability a vehicle is a car. How many cars do we have?
11.
I'm on 11 this time. You're on the other one, I think.
Yeah, I looked at the wrong one.
Okay, that's fine. 5 11s, does it reduce? No. What are we going to compare this to for our independence test? The probability of R or C. Go back up and look. It's always you're comparing it to the probability of the first one. So probability of red. Okay. How many red vehicles do we have out of how many total vehicles?
7 and 22.
Okay, I can go with that. 7 out of 22. Are 7 out of 22 and 5 out of 11 the same? No, they are not. So I'm going to make the statement that the probability of R given C does not equal the probability of R. Does that basically veto independence here? It does. We're going to go ahead and just practice and double check the other one. Reverse this. So we did probability of R given C. Now, what are you doing? Probability of C given R. On top, it's still both. So probability of C and R divided by the given. Go back and look at that formula if you're forgetting these. The given, which is the second piece, which is the R. Probability of C and R. How many red cars do we have? That was 5, right? Out of probability of red, how many red vehicles do we have? 7. What do I want to know if this equals? Does this equal the probability the vehicle is a car? So just your initial probability there, without the condition. What's the probability a vehicle is a car? 11 cars out of 22 vehicles. And 11 out of 22 does reduce if you want to be 1/2. What do we know? Yeah. Probability of C given R does not equal the probability of C. So because both of these are false statements, what are we going to say? Events R and C, they're not independent, so they are dependent. Okay. Debating, can we get through the next one or can we not? I want to try, but I'm not sure we can get through it, can we? So the next one will be one more practice at independent or dependent. Talking about girls and boys taking French. And so we'll look at girls and students taking French to see if they are independent or dependent. And I think we'll start with that tomorrow. And then we'll just look a little bit more at conditional probability and how we can use it to make a decision tomorrow. Okay? So we'll pick up there.